give time to Nathaniel Glasser. This is, again, one of our submitted papers that we wanted to spotlight. So Nathaniel, along with his co-authors, Yan-Cheng Liu, Junjiao Tian, working with Zolt Kira. So it's one of the submitted papers that's looking at how we can tie all of these threads together into a concrete application of trying to do data association and perception across multiple platforms. All right, so with that, I'll turn it over to you, Nathaniel.
Great. Yeah, thanks for the intro.
And we can see your screen and we can hear you, so you're all set.
Awesome. Yeah, thank you. Yeah, again, my name is Nathaniel Glaser. I'll be presenting our work enhancing multi-robot perception via learned data association. This work was done in the Ripple lab at Georgia Tech. Individual robots are susceptible to occlusion, noise, and other degradations. However, multiple robots grant us information redundancy. As you can see in the figure, the robot on the bottom left is unable to observe the target scene due to an obstruction. However, its partners have clear views. Intuitively, as humans, we know how to combine these two perspectives. Based on the unobstructed view, the letter to the left of B and C should be A. Our work explores how to encode the spatial contextual reasoning into a multi-robot perception pipeline. To this end, we asked the following question: how can we augment the visual observations of each robot with those of its neighbors? Specifically, we want to improve immediate egocentric perception, meaning for a single snapshot in time, how can each agent enhance its local inference, especially when it has access to the current observations of its neighbors? And actually, we have explored the task of collaborative perception in two other works from our lab. In these works, an agent must overcome full image degradation via compressed communication with its neighbors. These works also assumed known poses and hence known warping between viewpoints. On the other hand, for our current work, an agent must overcome localized degradation. Specifically, it must use the surrounding visual context to perform warping, and it must subsequently exchange compressed visual features to overcome this degradation. We call this new task collaborative perception via multi-agent infilling. In terms of scope, our work touches many domains. Image correspondence methods focus on matching visual features between frames. Optical flow and visual odometry methods perform a similar matching, though under stricter camera motion assumptions. In-painting methods hallucinate plausible outputs for missing image regions. SLAM methods focus on building long-term representations or maps. And multi-view learning methods seek to fuse often static viewpoints towards some shared perception task. Our work takes inspiration from these domains, while also introducing some distinctive twists. Specifically, we focus on the task of collaborative perception, where agents must share a compressed form of visual information. We use methods from image correspondence to identify matching context between two frames. However, unlike optical flow and visual odometry, we focus on a setting where viewpoints are often very different and weakly overlapping. And unlike most work in multi-view learning, we focus on a robotic setting where agents move through a dynamic environment. Unlike in-painting, we seek to overcome occlusions by not hallucinating a plausible replacement for the missing parts of an image, but by correctly extracting that information from supporting agents. And unlike SLAM, we focus on immediately improving local performance, not on building a long-term representation. Another distinctive feature of our work is that our method constitutes an end-to-end learnable solution. So what is our method? Well, to address our problem statement of how can we augment the visual observations of one robot with those of its neighbors, we came up with this simple formula. Basically, we add techniques from learned correspondence, image and painting, and semantic segmentation, and we raise this combination to the multi-robot power. And that gives us MAIN, the multi-agent infilling network. First, we adopt the learned cost volume approach of image correspondence methods. We compute a raw similarity volume between the extracted features of an agent pair. The argmax image on the left shows the best match of each cell in frame A to frame B. Notice the fuzzy rectangle in frame A is also reflected in this argmax image. This observation inspires our next design decision. Namely, we use methods from blind in-painting to contextually smooth and infill the similarity volume, not the raw image observations. We use a small convolutional encoder-decoder network to transform the noisy similarity volume into a smoother volume that can then be used for warping features. Next, we have our network work towards some perception task. In this case, we have the network produce a semantic segmentation mask. We use a variant on the SegNet architecture to produce this mask. Finally, we combine all these pieces together. Here we show the two-agent case. First, we compute a raw similarity volume between frame A and frame B. Then we smooth this volume. Next, we take the argmax of this volume across the channel dimension, which provides us with a map for warping features from frame B into frame A. Then with the original frame A features, the now aligned frame B features, we take the feature with the stronger matching score and forward it to the remainder of the SegNet architecture for semantic segmentation. Our method also extends to any number of agents. Here we perform context-based infilling and warping for each of the contributing feature maps. Then with the aligned feature maps, we use hard selection to forward the strongest spatial feature to the remainder of the network. So how do we test this method? Based on the proposed architecture, we need multiple views of the same scene. These are the only inputs that the network needs during training. However, during training, we also need per pixel image correspondences and the desired perception ground truth, in our case, a semantic segmentation mask. Luckily, a simulator can provide all of this information. Specifically, we use AirSim as our simulator environment. Within this environment, we collected a total of 6 views from a swarm of 3 flying robots. This dataset constitutes a relatively hard case for the multi-robot learning situation. The views are often non-overlapping and capture dynamic objects like cars and pedestrians. We have made this dataset publicly available. We further adapt this dataset into a multi-agent infilling variant. For this variant, we partially occlude one frame in the swarm, as shown in the figure on the right above agent N. Unfortunately, something is blocked in this frame, but we can use context clues to find the surrounding pattern in another agent. We can see that agent 1's yellow school bus is what is missing from the frame of agent N. So, at least for humans, there is sufficient information to infill the missing region. For a computer to learn this, we must provide a denser signal. In this case, we're able to use AirSim's pose and depth maps to compute per pixel dense correspondences. Additionally, from this variant, we introduced 2 dataset splits. The sequence split includes image pairs captured sequentially from each agent. This split has substantial overlap between frames and serves as a visual odometry sanity check. The cross split includes snapshots from all 6 agents. This split constitutes the multi-robot perception case, where there is intermittent and partial overlap between all observations. To evaluate our approach, we compute the mean intersection over union and mean accuracy scores within the degraded region of the image. We want to see how well the supporting agents can infill the degraded image region. We compared our main model against several baselines and performed an extensive ablation study. Here are some of the qualitative results. Each row represents a different dataset case. The left 2 columns show the inputs to our main model. The third column shows the infilling baseline that attempts to hallucinate a plausible output for the degraded region. The fourth column shows the output of our main model. Unlike the infilling network, the main model can capture correct scene details, like the window in the top row, the road hashings in the middle row, and the obstructed car in the bottom row. And here are some of the quantitative results. Our main model outperforms the baselines and ablated variants on both the sequence and cross splits. Furthermore, we notice an interesting trend. Most baselines perform well on static objects, for which there is a strong scene prior. However, the baseline models are unable to capture dynamic objects, since they only hallucinate a plausible output based on the scene prior. On the other hand, the main model is able to use surrounding context to exchange information relating to the degraded regions, and this success is reflected in its ability to accurately capture dynamic classes. So, in conclusion, we propose a variant on the multi-agent perception task, where robots must work together to overcome a localized image degradation, especially for large and dynamic viewpoint differences. We address this task via neural network architecture that uses context-based data association to exchange intermediate features within a segmentation network. And finally, we show that our network is able to learn embeddings that are suitable for cross-robot matching, generate a dense correspondence volume from these embeddings, and perform context-based smoothing, and use the smooth correspondence to exchange features that are then decoded to satisfy the final perception task. And for future work, we plan on looking into more realistic environments, more realistic degradations, improved fusion mechanisms across agents, and bandwidth reduction via handshake communication.